Hello, everyone. My name is Michael Humphrey. The Pechakucha you are watching is about the research that I, along with the help of several others, have been working on for 2.5 years. What we're trying to do is to create new drug molecules to treat cancer. Hopefully, you'll find it as interesting as I do. So, what is cancer exactly? Well, a regular cell mutates into a cancer cell, usually because of an external factor like how too much sunlight can cause skin cancer. The cancer cell will then stop functioning correctly and start reproducing like a rabbit on speed, causing a clump of cancer cells to form called a tumor. This tumor will then start attacking healthy cells. Because the cancer cells were originally healthy cells, the body has a hard time identifying them as a threat, which makes natural recovery very hard. Left untreated, cancer usually results in death, and this is why drug development is so important. When you first hear drug development, it can sound very intimidating, but it really isn't that bad. Just like anything else, you take a bunch of ingredients, you mix them, you cook them, and boom, you've created a new thing. Now, in chemistry, you do run the risk that the ingredients literally blow up in your face, but that's just what makes chemistry so much fun. Our first ingredient is 1,4-naphthoquinone. Not too easy on the eyes, he smells bad and he tastes worse, but he has a lot of the properties that we want. For example, the ability to kill cancer cells. He also likes to bond and has shown success in other drug molecules, so not at all a bad place to start. And here we see a list of our secondary ingredients, amino acids. In each trial, we use a different one of these, and we measure how the final product behaves to see if it's what we want. Lucky for us, because they are all amino acids, they share similar groups, and so they bond in much the same way. So we only need to develop one experimental procedure. Now let's talk about bonding. As someone who's been single for 21 years, I can assure you that trying to form a bond is hard. You have to actually meet the person you're trying to form a bond with, you have to meet in the right conditions, you both have to be in the right mood to form a bond, and many other factors. Well, molecules face all of these same challenges. So the first thing we have to do is to set the mood by making the reaction basic. Now that's a sciencey way to say that our solution will have a relatively low amount of positive hydrogen atoms. In these basic conditions, our amino acid will actually rearrange itself and become much more ready to bond with 1,4-naphthoquinone. The next thing we have to do is to get our molecules to meet up and to be excited about bonding. We can kill two birds with one stone by heating our solution. This causes our molecules to move around much faster, which increases the chances that they'll meet up, and then because they're excited, it increases the chance that they form a bond when they do eventually meet up. The final step in our synthesis is to add a catalyst, and our catalyst is cerium trichloride. The catalyst is essentially a wingman. He helps the 1,4-naphthoquinone hook up with the amino acid, but isn't actually in the final product. Without the catalyst, our yield is essentially zero, making this step very important. Now we have to see if our efforts to get these molecules together actually paid off. Unfortunately, it's not quite as simple as just checking their Facebook status or something. In order to see if these molecules hooked up, we have to do a variety of tests, but I'm just going to cover two of the simpler ones, TLC and UV. In a TLC, we place a very small amount of our product on a plate covered in powder and then place that plate in a solution. The solution will then crawl up the plate and move our product right along with it. Some molecules will be more attracted to the solution than others, so some molecules will move farther up the plate than others. Experimentally, this is what a finished TLC looks like. What we do is put a little spot with the starting material, a little spot with the product, and a little spot with both, all right next to each other. By comparing how far the spots are carried up the plate, we can tell if the molecule we ended with is different than the molecule that we started with. And the second test we run is an ultraviolet spectrum. We know that objects absorb some light and reflect the rest, and depending on what light they reflect, they will appear as different colors. This same concept applies to light that exists outside the range of light that we are able to see. By measuring what light a molecule absorbs, we get clues to its identity. Here we see an example of a UV test. From this graph, we can see that our product has an absorbance of around 1 at about 450 nanometers. Doing this same test for our starting material, 1,4-naphthoquinone, we don't see any absorbance at 450. This then signifies that our product is a different molecule than the one we started with. So after we do all of these various tests and confirm that we actually have a product molecule, we then have to purify it. We do this with a column, which is essentially just a giant TLC. We put all of our material in a tube on top of some powder, then we run a solution through the tube and collect all the fractions as they come out the bottom. So before we get to the stuff that actually matters, the results, let's make sure everyone is caught up. So far, we have decided that cancer is bad, and then we briefly covered how to make new molecules, test for those molecules, and then purify them. So we are now at the very important step where we see if these purified molecules can actually kill cancer cells. These scary looking graphs right here are how we can tell if our molecule works. The top graphs represent our molecule's effectiveness in Lewis lung carcinoma, and the bottom graphs represent melanoma. Basically, cancer cells are exposed to our molecules, and then we measure what percentage of the cancer cells die. If the lines and bars drop closer to 0, that's good. The problem we run into is that we have to make sure our new molecule doesn't do more harm than good. It's kind of like me pulling weeds in a garden. I try to only pull weeds, but I suck at gardening, so sometimes I'll accidentally pull up plants instead. Similarly, if our new molecule can't differentiate between cancer cells and healthy cells, then it's no good as a treatment. So our research is ongoing. We still have a few more steps to take. We still need to test its toxicity in healthy cells, and then comparing that with a great number of other things like availability, cost of synthesis, and effectiveness. Would our molecule be better than other drugs on the market? Or can we use it for something else? A scientist's work is never done. Mine is, though, and that concludes my presentation. I hope that you enjoyed it.